What's going on, everybody? Got another video here for you. This video here is directional derivatives and the gradient vector. So if you recall, we have done the partial derivative with respect to x and the partial with respect to y. And what did this give us? Well, that gave us the rate of change of z in the x and y direction. And in other words, in the direction of the unit vectors I and j. Okay, unit vectors I and j. Well, what if we wanted to find the rate of change of z at some x naught, y naught in the direction of an arbitrary unit vector? Okay, so if you see this, we have a surface S that has an equation z equals f of xy. This would be z equals f of xy. All right. And we let z naught equal f of x naught, y naught. The point p of x naught, y naught, p of x naught, y naught, z naught, this point right here, lies on the surface, lies on S. And there's a vertical plane that passes through P in the direction. So we've got this plane here that passes through P in the direction of our unit vector here. Okay, you see our unit vector right here. It intersects S in a curve C. And the slope of the tangent line from T, let's say T is here, to some point C. All right. At the point P is the rate of change of Z in the direction of U. So at this point P here, this is our rate of change. Okay, the slope of the tangent line in the direction of U. So we're not going in the direction of the x-axis or the y-axis. It's just some arbitrary vector. Okay, so that's what this section's about. All right, so let's look at this. It says the directional derivative of f at x naught, y naught in the direction of a unit vector u, a, b, that's what I kind of talked about earlier, is the directional derivative, this is the notation, equals the limit as h goes to 0 of f of x naught plus h a y naught, let's see, I left out a plus sign, y naught plus hb minus f of x naught, y naught. All that over h if this limit exists. Okay. So let's look at this example here. It says use the weather map in the figure to estimate the value of the directional derivative of the temperature function at Reno in the southeasterly direction. So you can see here they give us, they show us here this southeasterly direction. And what we have here, let me erase that so we can see it a little better. See, we're going here and this line's going to intersect there and there. Okay. So what we're looking for is where this line intersects these isothermals. And you can see it intersects it at 60 and 50. Okay, this isothermal line is 50 and this one right here is 60. So we have that's going to equal to, so it's the rate of change. So it's going to be the 60 minus the 50 over what? The distance between them. So that's the distance from here to here. And, you know, you're going to kind of estimate it. So you can see they give us a scale here. So it's a little more than the 50. You know, if you want to kind of estimate it, it looks like it kind of goes maybe about halfway in between. So if we turn that, it would, you know, if we turn that at an angle, it looks like that would be about it. So that would be over 75. That's the distance between those 2 points, approximately. So that's going to be 10 over 75, which is 0.13 degrees Fahrenheit. Per mile. And there's your answer. That the distance is in miles. And so, you know, that's all we're doing. Isn't the derivative a rate of change, right? See, they give us the direction that we're going here. All right, let's look at this. It says if f is a differentiable function of x and y, then f has a directional derivative in the direction of any unit vector u. Okay, so u is the unit vector, AB, and the directional derivative of f of xy, that's going to be the partial of f with respect to x times a plus the partial of f with respect to y times b. If the unit vector u makes an angle theta with the positive x-axis, then we can write u is equal to the vector cosine theta sine theta, and the formula becomes the directional derivative of f is the partial of f with respect the partial of f with respect to x times cosine theta plus the partial of f with respect to y times sine theta. All right, so let's use this to work this next problem. Notice here what they're telling us. They're telling us the angle that the unit vector makes with the positive x-axis. So, you know, if they do that, if they tell us the angle, then we can use this. Let's see. We can use this right here. All right, so it says find the directional derivative if f of xy equals this and u is the unit vector in the direction given by theta is pi over 6. Measured from the positive x-axis, what is the directional derivative of f at 1, 2? All right, so let's just go ahead and write the function down. All right, so what do we need? We need the partial with respect to x and the partial with respect to y. So let's just write the formula down. That's going to be the partial with respect to x times cosine theta, which in this case, notice they give us theta as pi over 6, plus the partial with respect to y times the sine of theta, and theta is pi over 6. And so this is going to give us, so let's take the partial with respect to x. So that's going to be 3x squared minus 3y times, and then what's the cosine of pi over 6? Well, that's square root of 3 over 2. Plus, now let's take the partial with respect to y. So that's going to be negative 3x plus 8y times the sine of pi over 6. So that's times 1/2. And so now let's just distribute. So we're going to get 3 square root of 3 over 2 times x squared minus 3 square root of 3 over 2 times y minus 3/2 x plus 8 over 2 times y. All right. So let's just come up here. Let's factor out a half. It might make it easier for us to evaluate pulling that 1/2 out. We don't have to worry about fractions except for that last one that we have to multiply. And so that's going to be 3 square root of 3 times x squared minus 3 square root of 3 times y minus 3x plus 8y. And so that's going to give us 1/2 times, that's going to be 3 square root of 3 x squared minus 3x. And then we've got what? Let's do plus 8 minus 3 square root of 3 times y. So I grouped the x terms together right here. I grouped the y terms together and then factored out a y. All right. So let's see. It says, and use the unit vector that measures from the point, and they want to know what is the directional derivative at 1, 2. All right. So we've got the directional derivative f of 1, 2. Make sure that, 1, 2. All right, so we plug the 1 in for x, plug the 2 in for y, and so that's going to give us 1/2 times 3 square root of 3 times 1 squared minus 3 times 1 plus 8 minus 3 square root of 3 times 2. And when you do all those calculations and everything, you're going to end up with 13 minus 3 square root of 3 over 2. And there's your answer. Okay, so that's your directional derivative at 1, 2. All right, so it says the directional derivative of a differentiable function can be written as the dot product of two vectors. So the directional derivative of f is the partial of f times a plus the partial of y, partial of f with respect to y, times b, which we can write this as this vector here, the partial of f with respect to x, partial of f with respect to y, dot ab. I mean, think about it. If you did the dot product, it would be this times this, which we have here, plus this times this, which we have here, which is equal to the partial of f with respect to x times the partial of f with respect to y, the dot product of that with what? AB, which, what did we say AB was up here? If I can find it. Let's see. Your unit vector, u. All right. So the first vector in the dot product, which is this one right here, is given a special name. It's the gradient of f, and this is the notation we use, the gradient of f. So let's look at this definition. If f is a function of two variables, x and y, then the gradient of f is the vector function, this notation, defined by the gradient of f is equal to the partial of f with respect to x, partial of f with respect to y, or we could write it like this in the ij form. Partial of f with respect to x times vector I plus partial of f with respect to y times vector j. All right. All right. So let's look at an example. Okay. Let's see what we got here. My screen's freezing up. All right, here we go. So it says, if f of xy is equal to sine x plus e to the xy, then the gradient of f of xy is what? All right. Well, there's your formula here. It's just the partial with respect to x, partial of f with respect to y, which this is what? Derivative of sine is cosine. And then the derivative of this is e to the xy times the derivative of the exponent, so that's y. Remember, when you're taking the derivative, the partial of f with respect to x, you're treating y like a constant. Okay, so the derivative of xy would be y. You should know how to do these partial derivatives. And then the partial of f with respect to y, well, derivative of sine x, that's like a constant. That would be 0. And then this would be x e to the xy. All right, so that's that. And then they want us to find the gradient of f at 0, 1. So we just plug the 0 and 1 in. So that would be cosine 0 plus 1 times e to the 0 times 1. And then 0, and that would be 0 times e to the 0 times 1, which that would give us cosine of 0 is 1. This is 1. 1 plus 1, that would give us 2, and then that would be 0. All right. So there's finding the gradient of f. Okay. All right, so we have a note here. It says we can write the directional derivative of f is equal to the gradient of f, or the dot product of the gradient times the unit vector. This expresses the directional derivative. I left off the AL. The directional derivative in the direction of a unit vector u as the scalar projection of the gradient vector onto u, of the gradient vector onto u. All right, so let's look at an example. So here it is. This right here is finding the directional derivative of a function at some point in the direction of, and notice how they give us this this vector here. We want to go in the direction of this vector. Okay. All right. So let's look at this. So remember what it says. The directional derivative is the gradient of f, the dot product of the gradient of f and the unit vector. Okay, that's what we're looking for at that point. All right, so we need to find the gradient of f. So we've got the gradient of f of xy. That's going to be what? It's the partial with respect to x, the partial of f with respect to x. So that's going to be 2x y cubed, and that's the derivative of this, minus, and then derivative of that is 0, and that's times vector I. I'm writing it in the ij form. Plus, and then the derivative of f with respect to y, that's going to be 3x squared y squared minus 4 times vector j. All right, so now we need the gradient of f at our point 2, -1. See, all I'm doing is this right here, this formula right here. That's all it is. Okay, and so that's going to be 2 times 2 times -1 cubed times vector I plus 3 times 2 squared times -1 squared minus 4 times vector j. All right, so I'm going to get -4i plus 8j. All right. Okay, so we've got the gradient of f evaluated at 2, -1. So what do I need now? I need the unit vector. So here's our vector v. That is not a unit vector. Remember, a unit vector, when you take the magnitude of it, you get 1. But remember, do you remember how to find the unit vector? Okay, so to do that, I need the magnitude of v, which is 2 squared plus 5 squared Let me write that a little better. And it's the square root of that, which is the square root of 29. So my unit vector is going to be 2 over the square root of 29 times vector I plus 5 over the square root of 29 times vector j. Remember, the unit vector of v is v times, or v divided by, the magnitude. Okay? Remember, let me write the formula here. Remember, your unit vector is vector v over the magnitude of v. And that's all we did there. Okay, so we just divided each one of these by the magnitude, which is square root of 29. All right, so now I can find my directional derivative f of, let's see, 2 negative 1, right? 2 negative 1 is equal to what? The gradient of f at 2 negative 1 dot u. It's the dot product of those two, which this would be, let's see, it's the dot product of this vector and this vector. So that's going to be negative 4i plus 8j dot 2 over square root of 29i plus 5 over square root of 29j. It's that dot product. And so this would give us, let's see, negative 4 times 2 over square root of 29. Right, it's this times this plus this times this. Five over square root of 29. And that would give us negative 8 plus 40 over square root of 29, which that would be 32 over square root of 29. And there's your answer. All right. So, I mean, it's really, it's not that bad. You've got to know how to take partial derivatives, and you got to know how to do the dot product, right? That's really all it is. All right, let's look at this, functions of 3 variables. Okay, so you can probably assume it's going to be similar to 2 variables. So functions of 3 variables, got the definition, the directional derivative of f at x0, y0, z0 in the direction of a unit vector u, so u is the unit vector, ABC, is this thing right here. Okay, I'm not going to read it all off if this limit exists. So, and if we use vector notation, you can write that as the vector x0. You can rewrite it like this, where x0 is x0, y0. If you're in 2 dimension 3, x0, y0, z0, or if you have, if n is 2 and this if n is 3, we can write this instead of all of this up here. Let's see, if f of x, y, z is differentiable and u equals abc, then the directional derivative of f of x, y, z is the partial of f with respect to x times a plus the partial of f with respect to y times b plus the partial of f with respect to z times c. For a function f of 3 variables, the gradient vector denoted by this is your gradient vector. Once again, it's just the partial of f with respect to x, partial of f with respect to y, partial of f with respect to z. Or we could write it in the ijk form. And so we have the directional derivative can be written as this. It's the same thing. It's the dot product of the gradient and the unit vector. Okay, All right. So let's look at an example. If f of x, y, z equals x sine y, z, so for part A, it says find the gradient of f. So we just want to find the gradient of f there. And then for part B, find the directional derivative of f at the point 1, 3, 0 in the direction of this vector v here. And you can see real quick that v is not a unit vector. All right, so for part A, let's find the gradient of f. So the gradient of f of x, y, z is equal to the partial of f with respect to x. So that's just going to be, well, what's the partial of f with respect to x? Well, that's just going to be sine y, z, right? I mean, x is our variable, sine y, z is like a constant. So it's just sine y, z. And then the partial of f with respect to y, so x is like a constant, z is like a constant. So that's going to be what? X, z times the, not the sine, times the cosine of y, z, right? Derivative of sine is cosine times the derivative of what you're taking the sine of. So the derivative of y, z is just z. And so you got your z times x. All right. That's a big thing here. You've got to know how to do these partial derivatives. All right. And then the partial of f with respect to z. So that's just going to be xy times cosine yz. All right. And there's your gradient. Okay, find the gradient of f. Now, for part B, they want us to find the directional derivative of f at this point in the direction of v. All right, so we've got our gradient vector. Now let's find the gradient of f at the point 1, 3, 0. So we just plug all that in. So that's going to be sine of 3 times 0, 1 times 0 times cosine of 3 times 0. And then we've got 1 times 3 times cosine of 3 times 0. And so this is going to give us the vector 0, 0, 3. Okay. So there's your gradient at 1, 3, 0, gradient of f. Now we need to find the unit vector. So, well, to find the unit vector, we need to do what? We need to find, keep hitting these buttons. We need to find the magnitude of v, which is 1 squared plus 2 squared plus negative 1 squared, and it's the square root of that. See, right? The magnitude. So that is going to be the square root of 6. And so we have our unit vector is equal to what? Well, that's going to be 1 over square root of 6 times vector I. Let's see, plus 2 over square root of 6 times vector j minus 1 over square root of 6 times vector k. So there's our unit vector. Okay. All right. So now our directional derivative, f of 1, 3, 0, is equal to what? Well, it's the gradient dot u. Okay, so there's our formula. And so this is going to equal, well, what was this? Well, this was the vector 0, 0, 3 dot our unit vector, which is 1 over square root of 6, 2 over square root of 6, and negative 1 over square root of 6. Doesn't matter which form you write it in. You can write it in the IJK form, or you can write it like this. It doesn't matter. Okay, and so this is going to give us 0 times 1 over square root of 6 plus 0 times 2 over square root of 6 plus 3 times negative 1 over square root of 6, which is negative 3 over square root of 6. And there's your answer. Okay, I mean, really, you know, when you start working these things, it's really pretty easy. It's not bad at all. All right, so let's look at this. We've got a theorem here. Suppose f is a differentiable function of 2 or 3 variables. The maximum value of the directional derivative is the magnitude of the gradient. And it occurs when u has the same direction as the gradient vector. All right, so let's look at an example. Okay. All right, so we have this theorem here, and when I was making the notes out, I evidently left out an example, and it's a pretty good example, so I had to pause the video and write the example. I wrote it on in another page, so we'll jump to that page and work that example before we work this one. Okay, and we're gonna use this theorem. They're gonna want us to find the some maximum values. So let's jump to that problem. We're using this. Let's look at this example. All right, so it says, so for part A, it says if f of xy is equal to x times e to the y, find the rate of change of f at the point 2, 0 in the direction from P to Q, where point Q is 1/2, 2. All right, so look, this right here is a problem that we've already worked. Okay, they're giving you the information a little different. That's all. They're not coming out and saying, here's your vector. They're just telling you to go from point P to point Q. Well, do we know how to find the vector from point P to point Q? Of course you do. You've done that. Okay. So we've got part A here. All right. So let's do the gradient of f. All right, so that's the partial with respect to x, the partial of f with respect to x. So that's going to be e to the y. And then the partial of f with respect to y, that's just going to be x e to the y, right? Derivative e to the y is e to the y. X is a constant here, okay? And then I need the gradient of f at 2, 0. Okay, so find the rate of change of f at the point 2, 0. So we're going to find the 2, 0. So that's going to be e to the 0, 2e to the 0, which that is going to be 1, 2. All right. Now, what do we need? In the direction from point P to point Q. So we need that vector there, right? So we have PQ, vector PQ would be what? That would be 1/2 minus 2 and 2 minus 0. And so that vector would be negative 3/2, 2. So there's your vector. So in the direction of this vector here. All right. So what do I need? Well, the directional derivative of f at 2, 0 is what? The gradient at 2, 0, which we have here, the dot product of this vector, and what? And the unit vector. Well, we need the unit vector. That's not a unit vector there. So we can find the magnitude of PQ, which is negative 3/2 squared plus 2 squared. It's the square root of that, which that is going to be the square root of 9 over 4 plus 4, which is the square root of 25 over 4, which is, what is that, 5/2. And so we have our unit vector is equal to what? Well, it's going to be what? Negative 3/2 divided by 5/2 and 2 divided by 5/2. There's our unit vector, right? It's each of these components divided by the magnitude. And so our unit vector will be what? Negative 3/5 and 4/5. Okay, so there's your unit vector. So I'm going to need to use, where is it? This vector and this vector. That's what I need, the dot product of those two. Whoop. So I've got the directional derivative of f at 2, 0. That is what? That's the gradient of f at 2, 0 dot u, which is 1, 2 dot negative 3/5, 4/5. Okay, and so this is going to give me negative 3/5 plus 8/5, which is 1. All right, so that's part A. It says find the rate of change at that point from point P to point Q. So the rate of change is 1. Now for part B, this has two parts to it. In what direction does F have the maximum rate of change? Okay. So let's go back over here to this one. So suppose f is a differentiable function of 2 or 3 variables. The maximum value of the directional derivative is this, and it occurs when u has the same direction as the gradient vector. Okay, so when it asks us in what direction does f have the maximum rate of change, okay, so it increases the fastest in the direction of the gradient vector, which is the gradient of f at 2, 0, which is 1, 2. Okay, we calculated that earlier. Where is it? Right here. All right, so that's that. And then it wants to know what is the maximum rate of change. What is the maximum rate of change? Well, if you remember here, there's your maximum rate of change. Okay, and so that's going to be the magnitude delta f to 0, which is equal to the square root of 1 squared plus 2 squared, which equals the square root of 5. So, I mean, we found maximum values, but, one thing I do want to point out here is in this problem, they just didn't come out and say, find the directional derivative at this point in the direction of this vector. Note in this problem, well, what do you got to have? You got to have the direction of a vector. And, well, what vector was it? Well, it was the vector between P and Q, so we actually had to find that. Okay. All right. So now let's get to our next example. All right, it says, suppose that the temperature at a point xyz in space is given by T of xyz is equal to 80 over 1 plus x squared plus 2y squared plus 3z squared, where T is measured in degrees Celsius and xyz in meters. In which direction does the temperature increase fastest at the point 1, 1, negative 2, and what is the maximum rate of increase? All right, so let's just write our function down. We've got T of x, y, z is equal to 80 over 1 plus x squared plus 2y squared plus 3z squared. Okay, there's that. So we need the gradient of t. So the gradient of t is equal to, so it's the partial with respect to x, the partial with respect to y, and the partial with respect to z. All right, so what I'm gonna do here is I'm gonna show you, I'm gonna write out taking the partial with respect to x, and then taking the partial with respect to y and z. It'll be similar. Okay, so I'm gonna come over here to the side. I'm gonna erase it, but here's one way. Here's how you can do the partial. So I could rewrite T of x, y, z as 80 times 1 plus x squared plus 2y squared plus 3z squared to the negative 1. And so if I take the partial with respect to x, well, the negative 1 comes down, so that's negative 80 times 1 plus x squared plus 2y squared plus 3z squared to the negative 2. All right, chain rule. Times the derivative of what's inside the parentheses. So that would be times 2x. And so this would give me negative 160x over 1 plus x squared plus 2y squared plus 3z squared, and then all of that would be squared. That would be your partial with respect to x. Now think about this. If you did your partial with respect to y, well, let me go ahead and write this down. That's going to be negative 160x over 1 plus x squared plus 2y squared plus 3z squared times vector I. Okay, so there's your partial with respect to x. If I was doing the partial with respect to y, okay, the partial with respect to y, well, it would be the same thing, but then when I do times the derivative of what's inside the parentheses, that would be what? Times 4y. Okay, so this would become what? 320. Okay, and it would be 320y. And then z would be the same thing. Okay, so now you know how to do that. So that's going to be negative 320y over 1 plus x squared plus 2y squared plus 3z squared times vector j minus, and then when we do the partial with respect to z, that would be 480z over, and that all would be squared. Be 1 plus x squared plus 2y squared plus 3z squared, and then that all would be squared times vector k. Okay, so I'm going to erase this where I showed you how to find the partial with respect to x, and then we also did it with respect to y. I didn't do the z. You should be able to do that. All right, so there's your gradient, and let's just go ahead and kind of rewrite it just a little bit. How about we go and pull out a 160 over 1 plus x squared plus 2y squared plus 3z squared squared. Let's pull that out. And we would be left with what? Negative x times vector I minus 2y times vector j minus 3z times vector k. All right, so we factored out a common factor of 160 over the 1 plus x squared plus 2y squared plus 3z squared, all of that squared. So now we can get the gradient of t at the point 1, 1, 1, negative 2. Okay, so let's find that. So that is going to be what? That's going to be 160 over, and then when you plug that into here, you're going to get 256. And that's going to be times negative I minus 2j plus 6k. See, I plugged the 1 in for x, so that's the negative 1. Plug the 1 in for y, so that's the negative 2. Plug the negative 2 in for z, so negative 3 times negative 2. That gives you the plus 6. All right. And what did they ask for? In which direction does the temperature increase fastest at that point? And what is the maximum rate of increase? So, well, there you have it. It increases, well, and look, and that right there will simplify to 5, the 160 over 256, that'll simplify to 5/8 negative I minus 2j plus 6k. So increases fastest in the direction, what? Negative I minus 2j plus 6k. And that can be your answer. So I know, you're watching this video, and I know you might be thinking, well, I'm fixing to type a comment and say, you left off the 5/8. We don't need the 5/8, okay? We don't need the 5/8, because what are we looking for? We're looking for the direction, and what direction does it increase the fastest? Well, this vector and this vector are going in the same direction. This vector may, this vector may be is a little longer. Okay, this is just a scalar. You don't really need the 5/8. We just want to know what direction is it going in. And if you wanted to, you could take this vector and find the unit vector and use that vector. Okay? Because it's not about the length of the vector, it's what direction, the direction of the vector. And this vector and this vector and the unit vector of this one, they're all going in the same direction. Okay? And then we have our maximum rate of increase. Well, what is that? It's the magnitude of the gradient at the point. And that's going to be 5/8 times the magnitude of times the magnitude of negative I minus 2j plus 6k. And so this is going to give us 5/8 times the square root of negative 1 squared plus negative 2 squared plus 6 squared. And that ends up giving us 5/8 times the square root of 41. And there's your solution. And that's actually degrees Celsius per meter. All right, there's your answer. So, I mean, look, all these problems we work, I mean, they're all worked exactly the same. You might have some problems where the derivative might be a little more difficult to take, be a little more difficult to find the partial derivative. Okay. All right, so let's look at this. So if we got the gradient of f, x naught, y naught, z naught, not equal to 0, the tangent plane to the level surface, f of x, y, z equals k at p of x naught, y naught, z naught at that point. As the plane passes through p and has normal vector, gradient of f of x naught, y naught, z naught, using the standard equation of a plane, we can write the equation of this tangent plane as the partial of f times the partial of f x of x naught, y naught, z naught times x minus x naught plus the partial of f of x naught, y naught, z naught times y minus y naught plus the partial of f of x naught, y naught, z naught times z minus z naught equals 0. The normal line to S at P is the line passing through P and perpendicular to the tangent plane. The direction of the normal line is therefore given by the gradient vector. That's the direction of the normal line. And so its symmetric equations are this. I'm not going to read through it, but that's its symmetric equations. So basically, I don't know, maybe I can kind of just do a real small sketch here. Something like this. And I know my drawings aren't good, but we might have something like this. We have some kind of surface here, and then maybe we have a tangent plane here at that point, at some point P, and then you have your normal vector there. Okay, your normal vector would be perpendicular to that plane at that point. Okay. This is your tangent plane here, and there's your normal vector. Okay. At that point. All right, so let's look at some problems here. It says find the equations of the tangent plane and normal line to the ellipsoid. X squared over 4 plus y squared plus z squared over 9 equals 3 at the point -2, 1, -3. All right, so we have f of x, y, z is equal to x squared over 4 plus y squared plus z squared over 9. All right, we got that. And we know here k is equal to 3. So you can see you have your f of x, y, z is equal to some k. And so that's what we have here. K is equal to 3 in this case. All right. So what do we have to find? Well, we've got to find the partial with respect to x, y, and z, the partial of capital F with respect to x, y, and z. And then what do we have to do? We have to evaluate them at that point. Okay. All right. And then you just plug everything into there. It's pretty simple. So let's find the partial with respect to x. Well, that's going to be what? X over 2. And then we've got the partial of f with respect to y. Whoop. That's 2y. And then the partial of f with respect to z, that's going to be 2z over 9. And then we're going to evaluate each of them at the point, at this point right here. Well, that's going to be what? Plug the -2 in, you get -1. And then fy of -2, 1, -3. That's going to be, plug the 1 in for y. Say y is 1. And then the partial with respect to z at negative 2, 1, negative 3. Now we're plugging in what? A negative 3. So that's going to give us what? Negative 2/3, because 3 and 9 will cancel. Okay. So now we have the equation of the tangent plane is, well, it's what? The partial derivative evaluated at that point. So that's negative 1 times what? Now remember, this is our point right here, x0, y0, z0. So it's x minus x0, so that would give us a plus 2. Plus 2 times y minus 1. Plus, not plus, how about minus 2/3, right? Times z minus negative 3, which would give us a plus 3, and that equals 0. All I did there is I just plugged it into that. And so then you can distribute the parentheses, all that stuff, and that is going to give you 3x minus 6y plus 2z plus 18 equals 0. And there's your tangent plane. All right. And then they want us to also, that's the tangent plane, and then they want the normal line to the ellipse at the point. So that's this formula. We've already found everything, so let's just bring this down here so you can see it. There's the equation for your normal line. And once again, we have the point what? Negative 2, 1, negative 3. We have our partials already calculated here. There's your x0, y0, z0. Plug everything in. So that's going to be what? X minus negative 2, which would be x plus 2 over the negative 1 here, equals y minus 1 over the 2, equals z minus negative 3, which would be z plus 3 over the negative 2/3. And there's your solution. All right. So I could probably end the video here. I mean, this example's not really any different, but it says find the tangent plane to the surface z equals 2x squared plus y squared at the point 1, 1, 3. So you can see here we can write this as 2x squared plus y squared minus z equals 0. So this is just showing you, get everything on one side, get the z over there, and in this case k is equal to 0. So you're going to do it the same way. Your f of x, y, z in this case is equal to 2x squared plus y squared minus z. That's really the only thing different, showing you move that z over, but then it's just work just like the other one, and we're just finding the equation for the tangent plane. We're finding the tangent plane. So we've got the partial of f with respect to x, x, y, z is equal to 4x, partial with respect to y, that's going to be 2y, and then the partial with respect to z is equal to negative 1. And so, I mean, when we evaluate at the point, I'll write it all out, and that's going to be 4. And then we're going to evaluate this at the point 1, 1, 3. That's going to equal 2. And then we've got this one evaluated at the point 1, 1, 3. Now that's just always negative 1. And so now we've got 4 times x minus 1 plus 2 times y minus 1 minus 1 times z minus the 3 equals 0. And then you can write this as z equals 4x plus 2y minus 3. Yeah, you know, if you wanted to, you could bring the z over and you set it all equal to 0. Okay, that's just, there's another way to write your equation for your plane. All right, so that was kind of a long video. I mean, you know, directional derivatives, they're not difficult to do. Basically, like earlier, you were doing what? You were finding the partial with respect to x, the partial with respect to y, right? That was giving you in the direction of the x and y axis. So that was going along those unit vectors I and j. Vector 1, 0, 0, and vector 0, 1, 0. But now what if we had any vector we wanted to go in any direction? That's what this is. All right. So I hope this video helped. Check out my other videos. Give me a like, share, subscribe, comment, and I will see y'all in the next one. Later.